I'm Angela Rasmussen from the University of Utah Electrical and Computer Engineering Department, and I'm going to go over an example of a parallel RLC circuit that is underdamped. So we're going to start with this circuit here, and in this we want to determine IC of T in the circuit. So the first step is, I've put it here, to determine if it's in series or in parallel form. And then from there, you need to determine alpha and omega naught. And then once you determine that, you're going to compare the two to determine, am I critically damped, underdamped, or overdamped? And so, and then once you determine those, you have a general form solution from the table in the book. And then you need to find the variables. So it will be initial values, final values. It could be the damping frequency, S1, S2, etc. Any other variables that you need to find those, and then you're going to plug it into the general equation based on what type of circuit it is, and how it transitions from the initial to the final state. So looking at this, you're going to determine the series and parallel form in the final configuration of the circuit. So for this one, the switch is closed at t equals 0. So that means that you have this circuit here. And hopefully you can see that the connection between the the capacitor and the inductor is what you're looking at. And above them, you have a extraordinary node connection. And so this is going to be a parallel form. So this circuit is parallel. So you can go and find the equation for alpha and omega naught, and then we're going to compare the alpha and omega naught. So alpha for parallel form is going to, again, be 1 over 2RC. And the R, again, is determined on this one by the final circuit. So looking at this final circuit, the independent sources, this becomes an open, this becomes a wire, and in parallel form, you're going to look at the inductor and ignore the capacitor. So the inductor becomes your A and B point, and then you're just going to ignore the capacitor, which means you can kind of remove it. So A and B is going to be here, A to B. And so looking at that, you can see if you go up from A, it splits and goes in two different directions. So 3 ohms is going to be in parallel with 6 ohms. So you have three ohms in parallel with 6, which equals 3 times 6 over 9, which ends up being 2 ohms. And so alpha is going to be 1 over 2 times 2 ohms, and C is given as 0.5 milli. And milli, again, is 10 to the minus 3, so make sure you include the units, and this ends up being 500 nepers per second. Now, omega naught is going to be 1 over the square root of LC, and L was given as 2 millihenries, and C again is 0.5 milli. And so omega naught ends up being 1,000 radians per second. So comparing alpha and omega naught, you can see that alpha is less than omega naught, so we're going to be underdamped. And so looking at the table, we're going to be underdamped with omega less than, or alpha less than omega naught. And so here's our general form equation. And now we need to find IL infinity, VL, initial value for VL, and then for underdamped, we're going to have that damping frequency omega D. And omega D is given by omega naught squared minus alpha naught, or alpha, can't talk today, omega naught squared minus alpha squared, then the square root of that. So we are going to need to determine all of those values. So I like to just usually start with omega D, which is that damping frequency. And what that means is that, remember that for underdamped, it's going to oscillate as it transitions from the initial to the final. So you're going to have an oscillation, and it's going to oscillate at that omega D value. So, and then it will usually either decay or it will increase and then do like a little ringing, but that oscillation will be at that omega D value. So we need omega D, so we can find, using just that equation, square root of omega naught squared minus alpha squared. And so in this case, our omega naught was 1,000 and our alpha is 500. So this gives us a damping frequency of 866 radians per second. So there's one value that we needed. The other values is the initial value. And so for the initial value, we need to find it at a time. And so we're going to do it at the time right before the switch happens. So that means that the switch is open first and then closed. So 0 minus is going to be an open. So we're going to have an open here, and that means it's been sitting for a long time. So a wire for the inductor and an open for the capacitor. And so with IL being in parallel to a resistor, remember that's called a bypass wire, and so it's going to short circuit the 6 ohms. So all of the current is actually going to flow through IL, and so you end up with no current in the 6 ohms. And and you're going to have 0 here. And so IL of 0 minus is going to be minus 6 amps. And then the initial value is actually found right as the switch changes. And so right when the switch changes, we're going to have the switch closed, and then IL is still going to be a negative 6 amps. And we want to find the voltage across the 6 amps. And this is going to be 0 because you have a wire in parallel with it. So that means that the VC is got to be also 0, which means, because it's again in parallel right after the switch, that VL of 0 will be 0. So those will be the initial values that we need. Is IL of 0, which is going to be a minus 6 amps. VL of 0 is 0. And then we need to find the final value. And so the final will be when the switch has been closed and it's been sitting for a long time, which puts this again at a wire. And so all of the current IL is going so we need to determine what IL is in this circuit. And so no current will be flowing through IC. again, that wire in parallel with the 6 ohms just is ignoring it. So there's no current also going to flow here. And you're going to have, I guess we could do a node. Let's see how to do this. So a node summation there. So we need to know what I1 is, and then IL, and then you have 6 amps going this direction. So I1 is going to be a plus 24 plus 3 times I1, and that's the loop right there. So I1 is going to be a minus 24 over 3, or a minus 8 amps. And so I1 goes out, IL goes out, and 6 amps goes out. And so plugging in minus 8 plus IL plus 6 gives me an IL of 8 minus 6, or 2 amps. So this will be the final value for the IL final value. So looking again at the equation, becoming big. For this equation here, we need D1 and D2. And so IL of 0 was, right, all of the values that we found. So IL of 0 was a minus 6 amps. IL at, sorry, this was miswrote, 0 was minus 6 amps. IL at infinity was, I think, 2 amps. Yeah, 2 amps. And then VL of 0 was 0. And so from here we can substitute these in. So IL of 0 was a minus 6, and then a minus 2 for a minus 8. And then VL was 0, so that will go 0. Alpha was 500, so we have 500 times minus 6 minus 2 over 866, and that gives a value of a minus 4.62. And then we have the IL equation, and so move this down so it's not right on my face. And so IL here is E. IL of t is e to the minus alpha, and alpha is 500. And then D1 is minus 8. Cosine 866 t. And then plus, or a minus, 4.62. Sine 866t plus 2. And these are in amps. So that is my IL of t. And again, we need to use IL of t to relate to IC of t. So looking back at the circuit, we see that IL of t, now we have a description, and IL of t is relatable to VL of t. And we see again that VL and VC are equal. And we see that VL is equal to VC. And then we know that IC and VC are relatable by C dV dt. And so we can differentiate this and it becomes LC. And then dVc dt becomes dIL dt. And so we can write this as LC IL double prime. So we need to differentiate this equation twice. And so doing that, and then we multiply it by LC. And so you're going to differentiate e to the minus 500t and then leave the cosine, and then you're going to differentiate the cosine and leave the e to the minus 500t. Same thing with the sine. The 2 amps goes to 0. And so you end up with IC of t is equal to e to the minus 500t 8 cosine 866t minus 4.62 sine 866t, and the other terms cancel, and that is your equation for IC of t. All right, thank you for watching.